Hello, everyone. Mr. Minix, my name. Math is my game. I'm joined today again by my first period Algebra 2 class. They're pretty excited because the Easter Bunny is coming to town. We're introducing Chapter 8, Section 2. In the title here is Graphing Rational Functions. Graphing rational functions. Easter's going to be, a week from Sunday, I think. So we're all excited because we're getting ready to go on spring break. But here we are, Chapter 8, Section 2, Graphing Rational Functions. I'd like to start with a real simple one, if we can. Is everybody down with that? What was the form for an inverse function? Y equals k over x? Wasn't that the form for an inverse function? What did we say about an inverse function? We said something about the origin with it, didn't we? It never passes through the origin. Never passes through THROUGH, the origin. Can anyone explain mathematically why that's true? Because it never hits zero, but mathematically, why is that true? Because the way the graph looks, kind of, but let's think about it. There's one thing in mathematics. Yeah, what do we got? As y increases, x decreases. Well, as x increases, y decreases. That's true, but mathematically there's a principle that we've talked about from the beginning of the year, from the time you talked about vertical lines and their slope, and when we talked about tangents of the north and south pole of 3 pi over 2 and pi over 2. It's undefined. What's undefined in this instance? What would happen if we plugged in a 0 for x or a 0 for y? We would get a 0 on the bottom and we'd have division by 0. Does that make sense? Okay. Yeah. And so if you plugged in a 0 here and a 0 here, you would have division by 0. I don't know how your skills are in proportions, but these two terms here in a proportion can actually switch places. So no matter what, you're going to get a 0, and that's not cool. There's a couple other things I could say that are not cool too, that somebody's doing right now that they shouldn't be. So if you need to sharpen your pencil, go for it. So here we go. Let's graph this new parent function. It's going to be y equals 1 over x. Y equals 1 over x. Now, I've told you before that I can't stand using tables. However, if we don't know what the graph looks like, a table is a fantastic thing to use. It's terrific. So let's get a table of values, x and y. And somebody might say, well, let's pick 0. Well, let's pick 0. 1 divided by 0 is undefined, so that's not going to work, is it? Dang it. Let's do 2. So if we had 2 for x, then our y value would be a hizzy. Good. What happens if we pick 1? We have 1 divided by 1, which is 1. Let's pick a hizzy. What happens if we had a hizzy? We would have 1 divided by a half, which would be 1 times 2 over 1, which would be 2. Interesting. Interesting. Very, very interesting. Let's do a third and see what happens. So if we had a third, we would have 1 divided by a third, which would be 3. And if we had 3, we would get a third. And then we'd have the counterparts of those where the x's and the y's would both be negative, right? So let's take a look at what that is going to look like. And I can't wait because we get to introduce a new word, a word that sounds bad, but it's actually okay. Ready for this? So what do we say? We said we went through the point 1, 1. What happened if we picked 2? Did we get a half or a hizzy? We pick 2, we get a hizzy. We pick negative a his, or we pick a hizzy and we get 2. So we pick a half and we get 2. We pick 3 and we get a third. We pick a third and we get 3. Do we see what's happening there in the first quadrant? So this is very difficult to sketch. I'm going to try my bestest. So we get that, right? It kind of looks like what's it look like? A quarter pipe? Yeah, like some kind of ramp. Now, we did say that we would get the negatives of all these too, right? So if we had -1, we'd have -1. If we had -2, we'd have negative a half. If we had -3, we'd have negative a third. If we had a half, we'd have, well, negative a half, we'd have -2. Negative a third would be -3. We get an idea what's going on there. So it's going to be a mirrored image of what we had in the first quadrant. Now, I don't know if any of you have ever been in the forest, but my nephew asked me a great question. He said, Uncle Matt, I wonder, how many trees do you suppose there are in the world? I said I would think there's at least 1 trillion. Anyway, yeah. The reason I asked about trees or brought up trees is this. Those parts of the graph, this part right here and this part right here, those have names. You know what they're called? They're called branches. Good. Those are referred to as branches. So is the graph a tree in theory? That's a good question. I don't think so. They just call them branches. I'm not sure why. Good question though. So what I'd like to talk about now is the domain of the graph. Now that's all the x values that can occur. I don't know if you remember this or not. I'll bet you do. You notice this arrow right here, and this arrow right here, and this arrow here, and this arrow here? It means it goes on forever and ever and ever. So it looks as though x can be just about anything it wants to be. So x is going to start at -infinity. Whoop. -infinity. Are there any restrictions on x? Is there something that x isn't allowed to equal? X isn't allowed to equal 0. So the domain's going to go from -infinity up to 0, but we're not going to count 0. And then on the other side of that, it's going to go from 0 to infinity. And we need to put these two, let me highlight these. We need to put these two things here and here. We need to say, well, it's those two combined. Does anybody know what symbol we use here? It's kind of an and symbol. It's a weird letter. It looks like the letter that people use for the word Y-O-U. There's a big U thing, yeah, right there. Okay. What do you suppose the range of this function is? The range of this function is going to be -infinity to infinity. Well, no, not -infinity to infinity. Because it can't go to 0 on the y either. So it's the same as the domain, yeah. So the domain and the range of this function are el mismo, the same. Now there's a part of the graph that I omitted, that I left off, because I'm afraid to say it. Well, the graph's not going to go through the origin. There are these imaginary lines right here and right here, and I need to define what those are. It's a word that sounds bad. The P is silent. It's not Price Pfister, the fabulous faucet with the funny name, or Michelle Pfeiffer. But the P is silent. Anyway, I'm going to define it, and then I'll show you what the word is. It's a line that the graph approaches. Now, there's something implied here, and I'm going to make it real clear. I'm going to actually write it out. It's a line that the graph approaches. The graph approaches it. What's that mean, to approach something? It gets closer and closer and closer toward it. If something's approaching something, does it ever touch it? No, not until it, yeah. So I'm going to put in parentheses here, but does not meet. It's kind of like a stranger. Total stranger, you're probably not going to go up and give them a hug. You might get closer and closer and closer to them, but you're probably not going to give a stranger a hug. Maybe you are. Depends on what they look like. Okay. Yeah. So here's the word. The P is silent. There are all kinds of mathematical joke t-shirts about it. The P is silent. The way it's pronounced, let me write it out phonetically. That's how you pronounce it. The P is silent. Asymptote. Why do they even have the P if it's silent? Ask Michelle Pfeiffer. Maybe she would know. So the P is silent. So our graph here has two kinds of asymptotes. It has the one that's going straight across. The one that's going straight across is called the horizontal asymptote. Horizontal asymptote is this one right here. So keep in mind, the graph approaches it, the graph gets close to it, but the graph never actually touches it. And then the one that goes straight up and down, what do you suppose that one's called? The vertical asymptote. Good. That's called a vertical asymptote. Okay. What do we think? So far, so good? Well, let's see if we can figure out two more ideas, and then we'll look at something that's in health class, and that'll be a good start for today. Yeah. So here we go. What if we graph y equals 1 over x and tack a plus 3 on the end of it? What do you reckon that's going to do to the overall graph? It's going to shift it up 3? That's exactly what it does. Holy moly, I can't believe it. We got this. Like a bows, like some bowses. So we knew that the regular graph kind of looked like this and like this, but you all said this one's going to be shifted up 3 units, right? And you're right. You're exactly, absolutely right. So we're going to take this graph. Yeah. So what we should do on our graph paper to make this easy to see is actually sketch in the asymptotes, because we know the graph's going to kind of look, this is an odd shape. What would you call that? Baseball stitches? Kind of looks like that. Draw a white circle around it. So anyway, that shape, we need to translate it up. So what I would recommend doing, because you're not going to have a smart board on your paper to sketch this, let's sketch in our asymptotes, right? Is our vertical asymptote going to change? No. So we still got our vertical asymptote like this. See ya. Have a great day. So what about our horizontal asymptote? Does it move? Does it get in a different place? We said it's going to be 3 up though, right? So here's our horizontal asymptote like that, and then our graph will look like that, right? Is everybody good with that one? Questions, comments, concerns? On the same graph, let's try to graph this one. Y equals 1 over x minus 2. How's that one going to be different? It's not going to translate down. Good try, though. Over to the right or to the left? You would think to the left, but it's to the right because it's counterintuitive. So on that one, it's going to be to the right 2, so that one's going to look like that. Make sense a little bit? One more graph to look at and to think about. Here's where we're going to end today, and we'll pick this up on tomorrow with the official notes. How could we make the graph do this? How could we make the graph do that? It's going to be y equals something over something. We would put a 1 here. We're trying to make the x values always positive. There's 2 ways we could do it. You got to think back to chapter 2 and 4. What could you do to x to force it to be positive? Flip it negative? If we graphed y equals 1 over negative x, that would actually just give us a reflection of that parent function we saw a minute ago, so that would actually just put the branches in the opposite quadrants. But we want, but x over 1, well then it's going to be a line, and it's not going to look funky like this. What can we do to force something to be positive? Maybe if I drive home 12 miles, I'll get an answer. Maybe if I long jump 17 feet, I'll have the answer. What am I mentioning? Distances. What's another way mathematically to represent a distance? What represents distance mathematically? What's that? There we go, absolute value. Good. That's one way to do it. That's one way. And the other way to force something to always be positive would be to, somebody said it. Nice, to square it. Good. If we squared it, it would actually grow a little bit faster. It would actually be a little bit steeper. But yeah, 1 over x squared would do it too. Okay, so we'll pick up there tomorrow. It's been real. It's been fun. I hope everybody has a good day. See ya. Shout out to Smiley. Shout out to who else? Will Duvall. Joe Emmerich. Fulton Dahl. Who else? Calvin. You're going to give a shout out to Calvin? Okay. All right. Calvin Kohler gets a shout out. All right. See ya. Good.